Washington State University. Go Cougs!
Welcome back to the course on behavior analysis from ambient sensor data. Here we are looking at activity learning, and in this particular module, we're focusing on feature extraction. Feature extraction is an important first step in activity learning. By feature extraction, we mean compiling a list of important values that describe not only a sensory event, but the context surrounding the sensory event. Once we assemble a list of feature values, we can use that as a single data point that provides a basis for activity recognition, discovery of activity patterns, and prediction of upcoming activities. In the previous video, we showed a demo in which a resident entered a home filled with ambient sensors. In the upper left, we showed all of the sensory events that were generated during those activities. And in the lower left, we showed a visualization of those sensory events. Each one of these sensory events provides information that we can use for activity learning and is characterized by the date and time when the event occurred, the sensor identifier, and the sensor reading. On this slide, we show the sensory events that were actually captured during that demo. We could use each one of these individual sensory events as data points for activity learning, but if we only use each one of these points individually, we miss out on quite a bit of contextual information that gives us additional insights for learning and tracking activities. So we will look at how to extract more context to provide more insights for our activity learning. Now, in order to fit the sensor data for our demo onto one slide, we reduced it a bit. We captured only motion and door sensors, removed all of the lighting and temperature sensors. In addition, recall that each of these sensor events included a date, time, a sensor identifier, and a message. We removed the individual messages and replaced the unique sensor identifiers with more general descriptive identifiers indicating what type of sensor this is and where in the home it's located. So our particular identifiers are the front door sensor, motion sensors in the entryway where the resident first enters the home, the hall that connects the entryway to the living room, the kitchen and the living room, and one additional door sensor is included, which is the kitchen cabinet sensor. Instead of treating every sensor event independently, we actually will look at an entire sequence of sensory events and extract features from that sequence, which we will refer to as a context window. So the first determination we have to make is how to divide our data into these context windows. There are several approaches that we can take. One approach is to actually segment the data into windows, one per activity. And this is possible if we know where each activity begins and ends, as would be the case if the activities were scripted. If we actually ask somebody to perform a specific activity inside an environment and told them when to start and stop, or noted when they started and stopped, then we can actually define a boundary around that activity. In this case, for example, we can see that we might be able to segment our data based on 3 different activities. One where the resident entered the home, as shown here. Another when the resident entered the kitchen to put away groceries. And the last when she entered the living room to start a 3rd activity. If the activities are not provided from an outside source, it is possible to apply activity or data segmentation to try to automatically identify transitions between activities. But another approach is not to segment the data based on activity boundaries, but rather use a sliding window. that's based on a data-driven criteria, such as the number of sensory events that we will try to fit in each window, or the duration of time that is spanned by each window. On our slide here, we have a total of 30 sensory events. So if we wanted a sliding window that was based on a fixed number of sensory events, we could, for example, have every window contain 10 sensory events, as you see here. Note that if we were to base the window on 10 sensory events, the amount of time that is spanned during the window would not be constant, because these are discrete event sensors that only report a message when there's a state change. Therefore, they do not arrive at constant time intervals. Now, once we define the sliding window size criteria based on the number of events or the amount of time, then we also need to decide whether we will allow these windows to overlap or not. If they overlap, we can extract features from one window and then move the window forward by a single event and repeat the process, creating another vector of feature values and thus another data point, and repeat the process again. We need to note that in this case, the individual data points are not independent of each other because they encompass sensory events that are in common between the windows. For the remainder of this discussion, we will assume that we are using a sliding window with a fixed number of sensory events. So we will fix it at 10 sensory events. Thus, we have 3 windows for our data. Now that we've identified the 3 windows from which we will extract features, let's talk about the specific features that we will extract. One class of features is based on the window as a whole and its characteristics, and these include the window duration, date, day of week, and time of day. In terms of window duration, we want to look at how much time is spanned between the first and last sensory events in the window. Again, this will vary based on the window because the events do not arrive at a constant rate. And the amount of time that is spent gives an indication of how active the resident might be in interacting with the space during that particular window. We compute the window durations here for each of the 3 windows in units of seconds. So we can see that from the last sensory event here, which occurred at 11:42 a.m. and 58 seconds, back to the first event, which occurred at 11:42 and 50 seconds, there was a span of approximately 8 seconds. In the second window, there was a span of 27 seconds, and in the third window, a span of 29 seconds. And again, that gives some indication either of how active the resident is within the space, how much they're moving around, or how much they're interacting with the space, depending on the types of sensors that are included. Next, we can look at the date and the day of week. In each of these cases, we need to consider which part of the window we're calculating these values for. It could be the first event, the last event, the middle of the window, or all 3. We, in our example, will calculate these based on the last event in each window. And we also need to decide on a reference point. In our case, it will be the number of days that elapsed since January 1st of the same year. Many reference points could be used. In fact, they could all be included in the feature vector. In our case, we're looking at February 22nd, which is 53 days since the beginning of that year, and is the same for each one of our windows. We will constrain our feature vector to contain only numbers. So instead of having a symbolic value for day of week, we will encode it as a numeric value where Sunday is a 0, Monday is a 1, and so forth. And 4 would indicate that this date is a Thursday. Lastly, we will encode the time of day. And once again, in our case, we will encode it based on the last event in the sequence, but it could be encoded for the beginning event, the last event, the average, or all of the above. We can also encode it in different granularities. We can encode the time of day as the number of hours past midnight, the number of minutes past midnight, seconds past midnight, and we include all three for each one of our windows based on the last event in each of the windows. Next, let's look at features that we can extract that give us information about each one of the sensors in our environment. For some of these, we will look just within the window, and for some of these, we will keep running information since the beginning of the data collection until the current window. The first is sensor counts. Here, for each one of these sensors that we have in the space, we will maintain a running count only within the window of how many times that sensor created a reading or a text message within the window. If we consider this as our list of sensors, front door sensor, entry, hall, kitchen motion sensors, the kitchen cabinet door sensor, followed by the living room, bathroom, and bedroom motion sensors, we can compute a quick count of each based on this window. For front door, we see 2 events corresponding to front door, so we encode that in our feature vector. In terms of entry, we see 1, 2, 3, 4, 5, 6 sensor events, as we've listed here. We see 1, 2 hall motion sensor events, and we don't see any other motion sensor events in this window. Here's the corresponding set of sensor counts for the second window and for the third window, and we can see that they are quite a bit different, and that gives us an indication of what the resident is doing during the corresponding time. For example, there are no front door or entry sensor events in the second window, so it's less likely that the person is leaving or entering the home in this window than in the first one. In contrast, there's a large number of events corresponding to the kitchen, whereas there were none in the first window, which makes it more likely that the resident is cooking or eating or washing up or putting away groceries. In this last window, we also see a large number of kitchen events. We see the introduction of a living room event as well, which did not occur in the previous windows. While sensor count was restricted to the events within the window, sensor elapsed time actually keeps a running count since the beginning of the data collection for each sensor, and it indicates the number of time units that have passed since a particular sensor previously generated a sensor event. Let's look at how these are calculated in the first window. In the case of the front door, and using the last timestamp in the window as a reference point, the number of seconds that have elapsed since the front door previously generated a sensor event is 58 minus 54, or 4 seconds. The amount of time that has elapsed since the entry motion sensor generated a text message until the end of the window is 1 second. The amount of time that has elapsed since the hallway generated a sensor event is 0 seconds, and so forth. The idea of sensor elapsed time allows us to distinguish between activities that might look very similar if we just had a small snapshot of sensor information. For example, if a resident enters a kitchen and opens a cabinet, they could be making coffee, as would be the case if there was a very recent bedroom event, meaning they just got up in the morning. They could be washing dishes, which might be indicated by motion sensors that occurred very recently in the dining room, meaning they just finished eating and are now cleaning up. Or they could be putting away groceries, as shown in this demo, and that might be indicated if the front door opening and closing are recent events. Additional features that we might consider are activity labels from previous windows. Using the example that we just raised, if we previously noted and labeled an earlier window as sleeping, Then the resident enters the kitchen. Again, it might be likely that they are making coffee in the morning, and we were able to get that from the contextual information that they were recently sleeping. If instead they were recently eating, then entering the kitchen and opening the cabinet might make it more likely that they are cleaning up after a meal. Another event that could be included, or another feature, is the change in activity level, or within what duration sensory events are being captured in the first half of the window versus the second half of the window. If, for example, there's very little activity in the first half, it's a large span of time for the first half of sensory events, versus a lot of activity in the second half, it could be that the resident is waking up from sleep or possibly returning home. Thus, there were very few sensory events over a large span of time. Similarly, we can measure the complexity of a window as the diversity of sensors that trigger sensory events within the window. If there's a large diversity, then it could be that the resident is moving quickly through the space as if they're putting things away or cleaning the home. If there's a low complexity, meaning a low diversity, then this might indicate that the person is in one place for a period of time doing a very focused activity. If we include numeric valued sensory events like our light levels and temperature levels, we can also add additional features that are statistically derived, like the maximum of these values, the minimum, the standard deviation, and so forth. More of these statistical features will be described in detail in the companion course on behavior analysis from mobile sensor data, where the values primarily are numeric. For our first window from our data collected during the demo at the beginning of the video, this is what our final feature vector would look like. But you can see that this is just the bare minimum of the feature vector. There are many additional features that could be used to provide context. This feature vector then comprises a single data point, and we will use this in the upcoming modules to describe techniques for activity discovery, recognition, and prediction.